Friends, this is our last session of this course, and today we will be solving some problems in reactor design. Now, if you recall, or you can always of course go back to your video lectures and recall if you do not remember. In the last module, namely the reactor design, we discussed several aspects. So, let us quickly summarize those and then look at few problems. So, what we started out was essentially looking at mass and energy balances for reactors in general, both tubular or fixed bed reactors, tubular reactors in which plug flow or small deviation of plug flow, that kind of flow is occurring, or a stirred tank reactor. And for stirred tank reactor, we wrote a general mass balance, so that we can emulate batch process, continuous process or a semi batch process using the same set of mass and energy balances, only appropriately changing the feed rates, where for batch reactor there is no feed in and out, for semi batch there is only feed in, but no feed out, and for continuous reactor there are both feed in as well as feed out. We then spent little bit of time for writing the mass balance as well as energy balance for heterogeneous reactions. We talked mainly about gas solid catalytic reactions here. So, here the idea is, firstly we recognize that not entire volume or the volume of the reactor is available for the transport in the bulk. So, if we write the mass balances for reactants and products in the bulk, all that bulk is experiencing is of course the convective transport and disappearance from the bulk due to diffusion into the catalyst. So, we wrote a very generalized scheme by writing a mass balance such that we say that there is some flux or there is some rate at which material is disappearing. And based on this, we had different types of models. For example, if we say that diffusional limitations are not there, then the disappearance rate or rate of those disappearance processes is same as the reaction rate. Therefore, what we had a pseudo homogeneous model. Model is very similar to homogeneous model, that is empty reactor models, except there is a void fraction term which appears. So, pseudo homogeneous model. But if you say that transport in the catalyst is also important, then we had this disappearance rate equal to the external mass transfer rate, because that is what only the gas phase will experience. It is sending out material from the bulk to the reactor, the catalyst surface, or receiving it if it is a product. But then what happens to this disappearance rate, which is essentially the mass transfer coefficient Kg into Cb minus C and that kind of equation, that has to be equated to number 1 the reaction rate if the reaction is only on the surface, or to the diffusive flux inside the catalyst pellet, that is diffusion coefficient D times dou C dou R or whatever the flux term is. And then we have to write the balance for what is happening inside the catalyst pellet, and for which we can use diffusion reaction equation, and therefore bring in our catalyst discussion into our reactor design portfolio. Following this, we looked at the energy balance in particular to see what happens when we have non-isothermal reactor operations. So, just as we have based on mass flow, we have batch reactors or continuous reactors, based on energy flow we can have two different extremes of reactions. One in which there is no energy removal from the system, an adiabatic operation, or the other one where energy removal matches with energy generation, thereby maintaining the energy content of the reactor constant, or in short temperature is constant or is fixed, and that is a isothermal operation. So, isothermal operation and adiabatic operations are two extremes of non-isothermal reactor design. We followed this up with few case studies, where we first of all looked at design of things like ethane cracking or hydrogenation of oil or ammonia synthesis, which led us to the kind of reactor operations which are not does not follow in the category of isothermal or adiabatic. This primarily arises for those reactions for which we have a reversible exothermic or even it is irreversible exothermic reactions, where we saw that there is a conflict between the kinetics and thermodynamics, particularly for exothermic reaction. The conflict takes this form. For attaining high equilibrium conversions, we need low temperatures, but to attain high reaction rates, we need high temperature. So, an isothermal operation with either high temperature or low temperature will not be good, because we will have to sacrifice on either one of them, either thermodynamics or reactor. On the other hand, if you have adiabatic operation, the temperatures will keep rising from the initial starting point if you are looking at a batch reactor or a fixed bed reactor. Then what will happen is initial low temperatures, low kinetics, as temperature rise, equilibrium is adversely affected even though reaction rates may increase, but again therefore we are in a situation where both kinetics and thermodynamics has suffered. So, we saw how we can overcome this problem by having, there are several ways. One of them was to have combination of adiabatic reactor followed by heat exchangers. So, you allow reaction to carry out in a adiabatic manner in a small bed, remove the energy that is generated. So, heat exchanger, follow it up with another small reactor, small bed, and repeat it, so that we get both high reaction rates and high equilibrium conversion. Now, we also saw that to achieve this, for exothermic reaction, for example, you have to decrease the temperature from inlet to the outlet of the reactor if you are using a fixed bed reactor, or from starting time to end time if you are doing a batch operation. But this also led to another type of operation, where the energy that is required to increase the temperature at the beginning of the reaction is the energy that is getting generated because reaction is proceeding. So, we combine heat exchange and reaction into a single step in a shell and tube kind of arrangement, only changing the flow pattern. That is, before reactants enter into reactor, they flow into through the shell in such a manner that the energy released from the reaction is taken up by the reactant molecules before entering the reactor, and therefore, they get preheated just for what we wanted. These operations we call them as autothermal operations. The third type of examples or class of examples we saw was, because of these non-isothermal effects, our reactors are having sensitive behavior, what we termed as parametric sensitivity. That is, a small perturbation can give rise to the reacting operation going from an safe to an unsafe operation, and this can take various different forms. For example, in a batch reactor, you could have that is the example of hydrogen combustion, a safe operation to a reaction explosion. In a tubular reactor, you could have, the example was xylene oxidation. You could have a case where what appeared to be a normal operation with temperatures all controlled, suddenly somewhere in the reactor the temperature shoot up to a very high value or runaway reaction, which could eventually lead to, if the material is not able to withstand those temperature rises, it could be catastrophic. Or in the stirred tank reactors, this led to what we call multiplicity of steady state, that is under same identical operating conditions we could have more than one steady state in our reactor. All these phenomena, you did not have to bring changes in the operating conditions of a significant magnitude. Few percentage point change in the cooling temperature or the initial partial pressure of the reactant or the coolant temperature in a tubular reactor is enough to go from a safe operation to an unsafe operation. Therefore, in design of reactors, it is essential that we identify these regimes a priori, so as to completely avoid this unsafe operation. Now, one may ask, why not go to the extreme and work in the regions when there is complete, even if there is a 100% change in the operating condition, nothing will happen, we will still have a safe operation. That is ideal, but unfortunately it turns out that most of the region where you get optimal performance of a reactor, be it in the yields or selectivities or conversions, is dangerously close to this boundary between safe and unsafe operation. Therefore, from practical point of view, we are forced to operate near that region, but with a caution that we should have good controls and detection systems. So, first of all detect the change in the operating condition and bring it under control as soon as it is detected. So, reactor design is invariably linked to good process control. We then summarized or concluded our discussion. So, we looked at this parametric sensitivity behavior, multiplicity, and therefore looked at how do we determine that when there are more than one steady state possible, are they all stable. Our definition of stability, apart from the fact that there are formal definitions, but practical definition is if you have a steady state and you have a small perturbation, and it is important that we can talk only for small perturbations, because our analysis was based on linearization of our non-linear dynamics. So, if we have perturbation and examine the performance of this perturbation, if that perturbation dies down, that means we return back to our original steady state from which it was perturbed, then we have what we call stable steady state. If not, we have a unstable steady state, that means this perturbation keeps growing. And there are formal ways, namely looking at the Jacobian of the dynamic mass and energy balances, looking at the eigenvalues of this Jacobian matrix at that particular steady state, and finding out whether the real part of the eigenvalue is negative. Then we have a asymptotically stable steady state. And finally, we concluded our discussion on reactor design by looking at how we can analyze the real reactors by using ideas of non-ideal flow, age distributions, exit age distribution, internal age distribution, cumulative distribution, how we can determine it experimentally and how it affects the performance of a reactor. We also saw that these age distributions or macro mixing alone does not determine the performance, because for the same distribution you can get two different kinds of performances depending upon whether the reactor fluid element or the material inside the reactor either interacts with each other or completely mixes or remains segregated or separated from each other. So, not only the residence time distribution or macro mixing, but the earliness and the extent of this mixing or interaction is equally important, or macro mixing is also equally important. So, with this summary, let us come to solving few problems on reactor design. The first problem that we will look at is an example of endothermic zero order reaction 3A going to 2B plus C is carried out in a batch reactor. The reaction mixture is initially heated up to 400 degrees centigrade. Reaction then proceeds adiabatically. During this heating period, 10 mole percentage of A is converted, and from this instant onwards, what is the time that is required to obtain 74% conversion of A, and then there is some data that is given. So, let us try to look at what is the important information that is given. Kinetics is 0 order, reaction is given, batch reactor, initial temperature, adiabatic reaction initially. During this heating period, 10 mole percent is converted. From this instant, that means what is the time that is required for 75% conversion of A. So, we need to find time, and we have been given heat of reaction, adiabatic endothermic reaction, the volume of the reactor, the specific heat of the reacting mixture which is given constant, the total mass, initial moles, and the rate constant, which turns out to be the rate of reaction because it is a 0 order reaction. So, let us try to work this problem out and look at how do we go about solving this. Our reaction is 3A going to 2B plus C, no change in number of moles. So, whether it is a gas phase reaction or liquid phase reaction, the volume can be assumed to be constant, and so with that assumption we can write the mass balance as dC1 dt equal to simply minus K, that is the rate of reaction. What about the energy balance? We can also write, since we have been given the total mass and the specific heat. So, energy content can be mCp dt by small dt, that is the energy accumulation term, which will be nothing but minus delta H into the rate of reaction into the volume of the reacting mixture, right. We have been given MT, Cp, delta H, K, V, everything is given to us. So, for the first part, we can write dt by dt as lambda into K, where lambda is minus delta H into V divided by MT into Cp. So, if you put all those numbers together, that works out to be 0.045. Okay. All the information is given to us. Mass balance, energy balance, they are related. So, we can put them together and say dt by dt plus lambda dC1 dt is equal to 0. Okay. So, with initial concentration at time t equal to 0, if you say that it is C1 0 and temperature is T 0, then we can integrate this equation and write T is equal to T0 minus lambda into C minus C0. Okay. Now, what was the first piece of information that was given to us? It was given to us that during the initial heating period, conversion is given. That means, we know the initial concentration, conversion is known. So, we know C naught, we know C, and this time the temperature will obviously go down because it is a endothermic reaction. So, knowing this energy balance, so what has been given? We know lambda, we know what is T, we know what is C0, and we have also been given this. So, from these 4 pieces of information, we can calculate what will be the T at the end of 10 minutes, because all this information is known, and that value works out to be 78.7 C. Okay. That is the information that is available. Now, what happens afterwards? Because what is the problem then? The problem is, we want to find out what is the time required for 70% conversion. Remember, we have been given only the rate constant at one temperature, that is 400. We do not know what is the activation energy and so on. So, now if we go back and look at our energy balance, is lambda into K. So, what I want to find out, what is the time required for 70% conversion. Okay. When the conversion is 70%, I can calculate what will be the temperature. So, I want to find what is the time. So, this one we can now write dt by dt, lambda value we know, and let us assume Arrhenius rate form for K. So, let us assume K of T is A e raised to minus E by R T, or we can write K of T with K of T at some reference temperature that is known to us as E raised to minus E by R into 1 by T minus 1 by reference temperature that is known to us, or in other words, using this information, the reference temperature that is known to us is 400. So, I can write one by T naught. The activation energy is also given or not, it should have been given. So, let us assume the activation energy is also given, otherwise we cannot solve this problem. Okay. So, knowing this, we can actually integrate this equation. This is exponential in temperature. If activation energy was given to us, it has to be given to us. So, the problem is, when conversion is 70%, we can calculate what should be the temperature, because we know this linear relationship. So, knowing this, at time t equal to 0, our temperature was something like 6 or 73 point something. So, what will be the temperature time when that new temperature, which was T naught minus lambda into C minus C naught, we know all these quantities. So, we can calculate that and find out the temperature. It is a fairly simple straightforward problem. Let us look at another problem. Okay, this problem and okay, this problem again let us look at this problem. A first order exothermic liquid phase irreversible reaction A1 to A2 is conducted in an adiabatic CSTR and in adiabatic plug flow reactor. So, we have two different reactors and we want to probably compare their performances. Both reactors are operating at steady state. Okay. So, we have been given adiabatic CSTR and adiabatic plug flow reactors. So, probably we want to compare the performance of these two. Both are at steady state, feed conditions are exactly identical, heat of reaction and specific heat can be taken as constant. We have to show that for both these reactors there is a constant relationship between concentration and temperature. Using this relationship, find out or sketch the rate of reaction as a function of temperature, and using this sketch show that for certain choices of feed and exit temperatures, the volume of CSTR will be smaller than that for plug flow reactor. So, let us see how we go about solving this problem. Alright, so we have a stirred tank reactor first. So, let us write down the mass balance. F prime into inlet minus outlet concentration must be same as K1 first order reaction, and the energy balance F prime rho Cp into T naught minus T is minus delta H R into V. Why? Because adiabatic reactor, so there is no heat added or removal term. So, now we can combine these two, assuming all properties are constant, and we will get C equal to C10 minus rho Cp by minus delta H into T minus T naught. What about tubular reactor? For tubular reactor, mass balance U dC1 dZ equal to R, rate of reaction, and rho Cp U dC1 dZ equal to minus delta H into R. Again, no heat added or removal term. So, we can combine these two equations, minus delta H dC dZ plus rho Cp dt dZ equal to 0. Okay. And again, if you take the same approach, we will get C equal to C10 minus rho Cp by minus delta H T minus T0. So, if we now compare the relationship for stirred tank reactor and for plug flow reactor, we have shown that there is a linear relationship only if properties of such as delta H, Cp, rho are constant. So, let us make that assumption, and let us call this constant alpha. Okay. So, what we have is C is C10 minus alpha into T minus T0. Okay. So, what is the next problem? So, we have got the linear relationship between C1 and T. Using this relationship, sketch the rate of reaction as a function of temperature. So, what we have is a first order reaction. So, rate of reaction is Kv into C, where Kv is a function of temperature, and from this relationship we also know K can be expressed as temperature. So, we can write this Kv as Arrhenius form into C10 minus alpha into T minus T0. Okay. Remember, this has come from this T. Now, what kind of reaction is given? Exothermic reaction. If it is a exothermic reaction, what is the sign of alpha? From here it is a positive number. What it means? What does it mean? In a reaction, reactant concentration is always going to decrease, and exothermic adiabatic reactor temperature is always going to increase. Okay, that's what we should keep in mind. So, what we have to sketch is rate versus temperature. Now, we do not have any numbers, so difficult to actually plot it, but let us qualitatively try to see how it will look like. Okay. Now, we know how rate will look as a function of concentration if temperature was constant, a linear curve, so it will always increasing. So, what it implies is rate is governed by these two factors Kv and C. Now, how does we know this? We also know that rate as a function of temperature is an exponentially increasing function, because as temperature increases the rate constant increases. We know all that, but our problem is to find rate as a function of temperature. So, first let us try to see how rate or concentration will change as temperature. So, here we take help of this equation. If my temperature is T naught or the starting temperature, let us say, what will be my concentration? Concentration will be C1 naught, okay, this value. Now, what happens as my temperature increases? Since it is an exothermic reaction, the concentration decreases in a linear manner. Okay. So, this is how concentration changes with temperature. Let us try to see how Kv changes with temperature, and we know this. There will be some increasing function like this, starting with T naught to a higher value. So, what we are interested in knowing is how the product of these two values Kv into C look like, because that is nothing but the rate. So, qualitatively we can see when T is near T naught, Kv is a low value, even though C1 naught is a low value, the product is likely to be a low value. When T is very large, Kv is very large, but C is very small. So, again product is likely to be again a low value. Kv as a function of time, temperature is a continuous function, C as a function of temperature is a continuous function. So, a continuous function which has low values at both extremes of temperature must go through a peak, and therefore, our rate versus temperature will look something like this. So, that is my sketch. Now, using this sketch, show that for certain reactions the feed or choices of feed and exit concentration, the stir tank reactor will be better than plug flow reactor. Now, how do we show that? Remember, this is my rate versus temperature. Now, let us go back to our mass balance equation for stirred tank reactor, along with the fact that C, which appears in this R, which is kV into C, is a linear function of temperature. So, what will be my energy balance? My mass balance, actually instead of mass I can work with my energy balance just to illustrate the same idea. So, for CSTR I can write that equation and you can verify it for yourself, rho Cp by minus delta H, which is actually our alpha value, into T minus T naught divided by R of T. And for plug flow reactor, this volume will work out to be A into U, cross sectional area into velocity, divided by rho Cp into minus delta H into integral dt by R of T from T naught to T. So, our usual method of comparing the two reactors, plug flow and CSTR, can conveniently be used for this case as well. What is that usual way? We see that it is determined by 1 over R. So, from this R versus, that is rate versus temperature, let us construct 1 over R versus temperature. It will be an inverted figure of this R versus temperature. So, we have this with T naught being this volume. Now, what is the volume required in a stirred tank reactor? In a stirred tank reactor, that volume is, for example, if this is my T naught and this is my T, desired T, then what will be that volume? T minus T naught divided by R of T. So, T minus T naught, that means area of this rectangle. So, this is my CSTR volume. What is my plug flow reactor volume? It is the area under the curve 1 over R versus T between the limits T naught to T. And what is that area under the curve? That area under the curve is this area. So, what will be the volume for plug flow reactor? This whole volume, the red color volume. So, now you can see for this plug flow reactor volume, which is area under the curve, is much larger than the reactor volume for stirred tank reactor. So, that is the case when stirred tank reactor is better than plug flow reactor. But what if my T naught was here? How do we determine those limits is what we are trying to look at. Suppose so this is my one scenario. Let us look at another scenario. If my T naught is here and my T, obviously temperature is higher than the inlet because exothermic reaction. So, what will happen to my reactor volumes? Now, let us look at the stirred tank reactor first. The stirred tank reactor, now the volume required will be 1 over R of T, that is this much, multiplied by T naught into T. That means, my reactor volume will be this entire area. I mean proportional, because there is a constant rho Cp by minus delta H. So, that constant is understood. Okay. Now, what about the plug flow reactor? For a plug flow reactor, area under the curve is now only this much area. I think I stand corrected. This should be f prime, and let us put it in the same manner, so that there is no confusion. We are essentially looking at the not the we are looking at the residence time. So, what happened now in this scenario 2? What do I see? I see that if area under the curve now is smaller than the area of this rectangle, that means plug flow reactor is better than stirred tank reactor. So, depending upon our initial choice of starting temperature, if it was up to here, and in fact all those cases where initial temperature was here or even little more beyond, we will find that stirred tank reactor is better. But for other cases, such as second case, the plug flow reactor will be better than stirred tank reactor. The third problem is actually very similar to what we just now saw. So, what was the reason why this behavior occurred, that stirred tank reactor better than plug flow reactor? The reason was that we had a rate and temperature dependency which was of this non-monotonic form. But this non-monotonic form can come from rate as a function of concentration also, and that is what this problem is. That is, a perfectly mixed stirred tank reactor is to be used for reaction and is operated isothermally. So, no temperature variations. The reactor volume is given, So, let us highlight the information that is given. The flow rate is given, inlet concentration is given, and the rate expression is given. The question is, it is suspected that the operation may have regions of unstable region with multiple steady states. Determine whether this is indeed the case. Outline the procedure to determine how the feed concentration should be changed, so that this problem does not arise. Now, let us try to look at this. So, what is this rate expression? This rate expression is what is actually shown here in this particular figure, and it is again a non-monotonic function. So, it is a isothermal. So, rate versus concentration is now a non-ideal behavior. So, what is our question? We want to find out whether there are multiple steady states possible, and how do we determine feed conditions so that multiple steady states do not occur? Okay, that is our problem. So, let us try to take a look at solution of this problem. Isothermal. So, we just need to look at mass balance, and if we take again our mass balance, F prime into C10 minus C1 is rate of the reaction, right, into the volume. We have been given F prime, we have been given C naught and all those quantities. So, we can actually write F prime by V into C1 naught minus C1 is equal to R of C1, and if you put all those values, R of C1 is 0.02 into 13 minus C1. That's just some number. Okay. We can of course put that R rate expression and try to solve for C1 and so on, but let's look at this solution in a graphical way. So, now graphical way means what? We have left hand side as a function of C1, we have right hand side as a function of C1. So, let us plot them, and the left hand side is already plotted, the rate versus C1. how will the right hand side look like? For this particular case, right hand side is nothing but the straight line starting with C1 of 13. So, suppose this is that 13, right hand side is 0. So, this is 1 point. What happens when C1 is 0? 13 into 0.02, that is 0.26. So, this is another point and a straight line. So, I will do my best to draw a straight line between these 2 points. So, what has happened? What will be the steady state solution when left hand side equals right hand side? So, let me draw it again with another color. So, what are the possible steady state? Steady state number 1, steady state number 2 and a steady state number 3. So, these are the possible steady state to this solution. So, again multiple steady state. Now, in this particular case, I will not go into the maths, but you can work it out yourself about the stability, for example. Remember, when we talked about isothermal non-isothermal reactor, we said that for those conditions under which rate of energy removal is higher than the rate of heat generation, we had a problem. That is or rather we had a stable steady state, and when the heat of generation slope was higher than the removal, we had an unstable steady state. Here there is no energy removal of generation, but what is it? It is mass generation and mass removal. If you look at left hand side, it is nothing but mass generation or rate of mass conversion or the rate of reaction, and the right hand side is nothing but mass in and out, net mass added to the system or removed from the system, whichever way we want to look, and the steady state is a balance between the two, which is what we expect. So, based on the discussions that we had, we can safely say, and you can verify it, that 1 and 3 are stable and 2 is unstable. Once again, how do we verify it? So, let us say that we have this steady state number 2 and we introduce a perturbation. What will happen? In this particular case, the rate of conversion of one species is lower than the rate of its net addition. So, what will happen? Concentration will keep on increasing and we will come to this particular steady state, and same thing can be argued if the perturbation is in the reverse direction. So, now how do we determine how to avoid this? That means, the intersection of these 2 points, these 2 curves, right hand side and left hand side, must be a single point. What does it depend on? It depends upon the slope 0.02, but what is our question? We want to find out under what conditions feed concentrations it should remain unchanged. So, we keep feed rates same, but we change this feed concentration from 13 to a different value. So, suppose I make it 8, okay. The slope is same as this blue line and 8, so 0.16. So, we will have this as an operating line and the intersection point is only 1. So, between 8 and 13, 8 we had only, that is feed concentration, that is C1 naught equal to 8, only one steady state. If our C1 naught is 13, we had 3 steady states. So, between these two there must be a point where we shift from 1 steady state to 3 steady state, and what would that point be? That point would be where this operating line with a slope is just tangent, that is, that straight line is tangent to our reaction rate curve, that will be one limit. But that tangent can be found at two different locations. So, another tangent over here. So, in this feed concentrations, you can work out what those exact numbers are. In this regime, we will have 3 steady state. Any feed concentration on this side, if you do, you will have only one steady state intersection. So, anything here or here, single steady state, but all those concentrations in between, we have 3 steady states. So, again you can calculate the multiplicity by actually calculating the eigenvalues and so on. In this case, it is only one dimensional. So, eigenvalue calculation is even more easy. So, with this we will come to the conclusion of our course by looking. So, the last lecture was essentially looking at some problems. I thoroughly enjoyed giving these lectures. I hope you find them useful too. Thank you.